So normal limit properties, if you were to substitute the 0 in for direct substitution, do you see that you would get 0 squared times sine of 1 over 0? But why can't we use the normal properties? You can't have 1 divided by 0. So 1 divided by 0 is undefined, so you can't, right? Okay, so we're going to sandwich this between two things so that we can actually calculate the limit here. Okay, so what two values is sine x, for instance, sandwiched between? Think of the sine wave. Yes, 1 and -1. Very good. Okay, so what about sine of 1 over x? If you were to, how would that change? Would that change at all? No, because sine values always have to be between -1 and 1, right? Okay, so what happens if I change, what is this called, remember, in trig? If I put a number in front of the trig ratio? The amplitude. If I change the amplitude, how would that change how I corral? Yeah, it would be -3 and 3. Very good. And same with if it was a half, it would be -1/2 and a half. And what about if it was k? -k and k. So you get the gist of what's going on. So now, using these ideas, I have this x squared here. So x squared is kind of like acting like the k there. So what would this be sandwiched between? -x squared and x squared. Okay, so now we're going to talk about limits here, okay? So what is the limit as x approaches 0 of the lower bound? Meaning, what is the limit as x goes to 0 of -x squared? So think about that. Even if you don't know how to do this algebraically with direct substitution, does everybody remember what -x squared looks like graphically? Yeah, it's an upside down parabola. So what's the limit as x goes to 0? It's 0.
Oh, yeah.
Yes?
Yeah.
Okay. And what about the other limit? The limit as x goes to 0 of positive x squared. I don't need a bracket, I guess. Positive x squared. It's still 0. So let's actually physically graph this just to see. So I'm just going to pause. So graphically, you can see that the x squared sine 1 over x is sandwiched between the positive x squared and the -x squared. Does everybody see that? So when we're doing the limit as x goes to 0, if it's sandwiched between those two, that means this equals 0. The limit is squeezed, or you can say sandwiched between the other limits of -x squared and x squared. Okay, so that takes us to your first official theorem of the course. So if they ever ask you a question and you know you have to use the squeeze theorem, you have to justify it by making sure it meets the criteria. They actually don't give you any marks if you just state this is the squeeze theorem, therefore the limit is 0. You actually have to state specific things to get your full marks. So the squeeze theorem says if f, g, and h are continuous functions on some interval containing a, and f of x is between g of x and h of x, that means you're kind of you're corralling on that same interval. If the limits are the same, then because they're in between each other, that means by the squeeze theorem, it equals that limit as well. Yes, so we're going to do that. Don't worry. So here, I put this in like a box so you can actually see that you have to, what you have to state. So you have to verify both conditions, and the both conditions is it has to be continuous. You have to actually write they are continuous functions. And that they have to be between each other. And then you have to state what the upper limit and the lower limit was. Oh, sorry, identify what the upper bound and the lower bound is. And the limits, and then draw the conclusion. So sometimes like on the Khan Academy, I'm pretty sure they do a lot of tables on the Khan Academy, right? The way they trick you, and I don't know about Khan Academy, but I know the way the AP board will say, they'll have this will be on a multiple choice, and one of the multiple choices will say, like, you can't determine it because there's not enough information. And sometimes it's true. The problem is they have to say it's continuous here, right? And then you have to be able to, you have to know somewhere they have to state that the function you're talking about is in between. So those are the two conditions that have to be met. It has to be continuous, and you have to either it's stated that they're between each other, or graphically you can see that they're between each other, or you have the y values that you can sandwich them between. So then once you establish that, then we can actually find the limit. So this is, I'm going to write it out here. Okay. Since f and g are continuous functions, because it's stated, right? And k of x, f of x is between, or is less than or equal to k of x is between g of x. And now I got to state what the limits are. So, and that they're equal. So then the limit as x goes to 1 of f of x equals what? 1. Oh, sorry, 1. Because that's what they're asking you to do, is when x goes to 1. So what is it equal to? It's 11. And that is the same thing as the limit. You can do it as two separate, but sometimes it's just easier to do this. Does everybody agree that that's the same limit at g of x? So again, I state the two conditions. I state the equality of the two limits, then by the squeeze theorem. So let me see if my grammar is good. Since that and that are continuous, and that, then by the squeeze theorem. Again, you don't have to actually state the squeeze theorem for full marks, but it's probably better, just for your own sake. By the squeeze theorem, the limit as x goes to 1 of k of x equals 11. So it's a pretty easy concept. It's just that you have to know what you have to say to get full marks. I think when I looked at the quiz for the Khan Academy for this, is like they'll say like Katie did this, and so what does she have to verify to use a squeeze theorem or something like that? Okay, suppose that we have some function g of x and cos of x. So g of x is between cos of x and x plus 1 squared, where x doesn't equal 0. Determine the limit as x goes to 0 of g of x. Okay, so whenever you see an inequality like this, it should be almost like a red flag. Oh, this is the squeeze theorem. Okay, let's do what we have to do. So what do we have to do? We have to say they're continuous. So is cos x a continuous function? Yes. And yes. So you just got to state it. So since, let's call it f of x. So f of x equals cos x, and h of x equals x plus 1 squared are continuous functions. Because they're polynomials, and trig are all continuous functions, right? The next thing we have to do is we need to state that they're between each other. And so here's another thing about the AP College Board. If I have specified that f of x is cos x now, I don't have to write cos x. I could actually write it as f of x now, because you've actually told me what it is. So you could say, and f of x is between h of x. You know what I mean? Like, you can write it like this if you want, if you want, or you could write it as those. But you'll see later on in the course, sometimes some of the functions are so long, it's better to refer to that by just f of x or whatever, as long as it's somewhere it's specified what f of x is. Okay, so we said they're continuous. We said they're between. Now we need to do the limits. And the limit as x goes to 1 of f of x, which is the cosine. Oh, sorry, it's not 1, it's 0, right? Yeah. So the limit as x goes to, should I write cos x or f of x? Doesn't matter. It doesn't matter. Okay, so x goes to 0 of f of x. So picture the cosine graph. Yes, it's equal to 1. And picture h of x. This is a parabola that got what? Left 1. Do you know what the height is? So here's your thing, and it went left 1. Remember your 0, 0, 1? Yeah, it's 1. Yeah. Okay. So that equals 1. Then, by the squeeze theorem, the limit as x goes to 0 of g of x equals 1. Like I said, it's not hard. It's just, you know. Okay. Oh, yeah. Important. We're getting to an important part of this title for this lesson was Squeeze Theorem and special trig limits. And so this is a special trig limit that you need to, again, this will go into your memorization thing. So I'm just going to show you using the squeeze theorem that sine x over x is equal to 1. And we're going to do it, again, let's do this graphically. So we're going to graph cos x, we're going to graph 1, and we're going to graph sine x over x. Does everybody understand when the limit goes to 0 of sine x over x, you would get, you can't figure it out, right? The sine of 0 is 0, and then you get 0 on the bottom, so you get 0 over 0. Can't do it, right? Okay, let's get our calculator. So visually, you can see that the limit is 1, right, when x goes to 0 of it. So now we're going to actually use the squeeze theorem to prove it. So again, what's the things we have to say? Yeah, so since g of x and h of x, oops, h of x are continuous. I guess we could have said continuous functions, and like we verified that it's between. So let's name, I should have named here, hey? Well, I could do it this way. How about this? What's on top here? What's the bigger one? Yeah, 1's on top, so I have to have cos x first. So cos x is between sine x over x is between 1, yes? And then what do I do after that? The limit? Yep. So the limit as x goes to 0 of cos x, and I could have stated as g of x, doesn't matter, is equal to what? 1? And does everybody see that's the same thing as the limit as x goes to 0 of 1? That was one of the things we learned. Yeah. Then, by squeeze theorem, the limit as x goes to 0 of sine x over x equals 1. Okay, so this is actually something you need to memorize. Not how to prove it, but that this special property of trig, if you have it in the setup of sine x over x and then the limit is going to 1, sorry, the limit's going to 0, then it's equal to 1. Yeah, and just even if you don't believe me, it's equal to 1. I could remove from my calculator sine x over x and put it as x over sine x, and I will get it sandwiched in the same spot. It'll just be slightly different. Well, let's do it. Okay, so, oops, where am I now? There we go. Okay. So, again, visually, you can see that the limit as x goes to 0 of h over sine x is 1 as well. So the goal here is to create the sine x or the sine h. I use h because it doesn't have to be x. It could be 4x. It could be 10x. It doesn't. It just has to be whatever is on top has to be the same as the bottom. So once you have that, that's equal to 1, and then you can go from there. So does everybody see I have a 4x there? So you can't get rid of the 4 because the 4 is inside the sine function, right? So I'm just going to make it look like there's a 4. So I have an x there. I'm just going to put a 4 there. Do you see I have now the setup of sine h over h? It's the same thing on top of the bottom. I can't just do that, though. So what do I do to compensate? Oh, come on, you guys. Yeah. Yes. Does everybody see I can do that? That's legit because the 4s would cancel. I have exactly what I had before. Okay. So does everybody see? And one of the properties of limits, right, was this is like a constant multiple, right? It doesn't matter if I do this first and then multiply it by 4 after or before. It doesn't matter, right? So what is this equal to? 1, and 1 times 4 is 4. Are we good with that? Okay, so again, the goal is to have sine of something over the same thing. Like it could be a happy face. The happy faces have to match, right? Okay, so the limit as x goes to 0, we have sine of 2x. So I'm just going to scooch the 6x over here. Actually, I'm going to leave the x here. I'm just going to scooch the 6 over here. Does everybody see that's still the same question, right? Okay, so now what do I have to place to get that set up? I have to have the 2. Again, I can't just do that. So I put the 2 in the top. So this is equal to 1. 1 times 1/3 equals 1/3. What do you think about this? Not too bad, hey? This one's a little bit different, though. This one's got an addition in between. So you got to remember now, what can you do here? Huh? No, you can't. No. No. You got to split up the fraction. Okay, so the property of limits, you can separate addition, right? Okay, so we know this from, especially we went over this in Trig, that this would be the same thing as the proofs. This is the same thing as sine of 2x over 3x plus the limit as x goes to 0 of 7x over 3x. Is everybody good with what I did? Like that's the same thing. Do you agree it's the same thing? Yeah. No? Okay. So I got to do some manipulations here, right? So the limit as x goes to 0 of sine 2x, I'm going to put the x there. I'm going to scooch the 3 over. That's still the same. I'm going to leave this for right now. So what do I need to put on top? I need a 2. So I'm going to do a different color. I need a 2 here and a 2 there. Now I have the setup. Okay. So then plus here, if I have an x on top and an x on the bottom like this, what do you want to do? Cross them out. So this is really the limit as x goes to 0 of 7 over 3. Does everybody see I can cross that out, off there? So what's our answer? Well, this is 1. 1 times 2/3 plus, what do we get here? What do we get here? What's the limit of a constant function? It's just that, right? Well, it's the same thing as the 1. If you have y equals 1, what's the limit no matter where you are? 7/3, although it looks like goofier than 1, it's still a constant function, right? It's just 7/3. Yeah. So 2/3 and 7/3 is 9/3, so that equals 3. Okay, next one. Do you want to try this one?
Sure.
Yeah?
Which one is that?
D, I'll give you a hint. You need to scooch this sine 5x into another fraction to get the setup. Okay, so I'm going to write it like this. And okay, so limit as x go. I'm going to write it as one limit. Are you okay? So sine of 2x. I'm not going to put sine 5x there. Okay. Then I'm going to put sine 5x right here.
Oh, I see. That's what I did. I got 2x. And you're going to break it up.
Okay, so now I'm going to put what here? At 2x. So what am I going to do to compensate it? I'm going to put the 2x over there, though. Because what do I need up here? We need a 5x here. So I put a 5x there. Because I need to have this set up here. Do you see? And then these cancel. So what's this equal to?
Equal to 2 over 5.
1 times 1 times 2 over 5. Yes, so it's 2 over 5.
Oh, yeah, that's true.
Yeah. Okay. So what do you think the limit as x goes to 0 is tan x over x? So what's tan x equal to?
Like for x goes to 0, it's sine x over cos x.
Yeah, it's equal to sine x over cos x, right? So I'm just going to, I ran out of room here. So the limit as x goes to 0 of tan x over x is the same thing as the limit as x goes to 0 as, I'm going to write sine x over cos x over x. But what did we learn, like with these fractions? Yeah, keep change flip. Keep change flip. Okay. So this is sine x over x cos x. Okay. What can I do with this? I can scooch it over. So this is the limit as x goes to 0 as sine x over x times 1 over cos x. So this is 1. Yeah?
Yeah.
And what is 0 when it goes into here? What's cos of 0? 1. So this is 1 times 1 equals 1. So you don't need to do this anymore. You can just say it's equal to 1 and now memorize that. No, you don't have to show this. I'm just saying now I've just proved to you that tan x over x is the same thing as sine x over x. No, I want to ask you to prove is memorize that if it's the same setup for sine x over x works for tan. It doesn't work for cos, but it works for tan. So, do you want to try this one?
No.
You can do it now, right?
No.
Yes, you can. Okay. So okay, so I'm going to set up the tan 4x over. Now, this 2, I'm just going to move the 2 over and leave the x there. You don't have to do it this way, but that is one way. This is still the same question. So then just put a 4 there. I'm going to do it in a different color. A 4 here and a 4 here to compensate. There's your 1. 1 times 2 is 2. Okay. All right. Now, I'm going to prove to you what this limit is here, okay? So what I'm going to do here is I'm going to multiply the conjugate. You guys remember what the conjugate was again? Yes, 1 plus cos x. Okay. 1 plus cos x over 1 plus cos x. Okay, so then I'll get the limit as x goes to 0. What do I get on top here when I multiply that? FOIL it, right? FOIL it. 1 minus cos squared x over x bracket 1 plus cos x. I'm sorry? It's the same as sine squared x, yes! Okay, so this is the limit as x goes to 0 as sine squared x over x 1 plus cos x. Yes? Okay, so can you picture the sine x setup here? This is sine squared. So watch this. So limit as x goes to 0. Instead of writing it as sine squared x, I'm going to write it like this. Does everybody understand that's the same thing as that top right there? The sine x squared, the whole thing squared is the same thing as sine squared x. You learned that in grade 12. So what do I write at the bottom? Well, I have to put an x there. No, well, yeah. But so essentially what I did by putting the x there. Stop. Okay. So because I put an x here, I got the setup I want, right? The sine x over x. However, it was only one single x there before, but really I have two x's there. So what do I have to do to compensate? What do I have to do to compensate? Put a what where? Put an x there, right? That would compensate. Does everybody see if I were to square this, I have an x squared at the bottom, and that x would cancel the x squared at the bottom. I'd still have the x, which was the original thing. And then this will be over 1 plus cos x. Is everybody good with what I did? It's kind of crazy, but yeah. Actually, I should do this in red colored pen because that was from the beginning here. 1 plus cos x. Okay, so this is the extra x that from this extra x here. Right. No, it's not just, I put another x down here, but I just didn't write it because it's got the square here. You know what I'm saying? You could also notice it as this is sine x times sine x, and I only have one single x. So in order to put an x here, I have to put an x there. Do you see? That's the same thing as this. Okay, I'll repeat what I just did. Okay, so watch again, okay? The sine x over x, sorry, I'm going to get rid of this x, okay? Does everybody agree? Sine x times sine x over x is the sine squared x. Okay, so now I'm going to put an extra x here, and then to compensate, I'm putting the x there. But this together collectively is that, right? Does that make sense to you now? Okay, I didn't just like throw just one x there. I actually did an x and an x diagonal from each other. Okay, maybe I should have wrote it like that and it would have made more sense. Okay, so now, does everybody see? And maybe I should, maybe I'll show this in the other class. I'll show it this way. See, I always get better. I get better every time I do this, right? Okay, so I still have this x on top, and then I have the 1 plus cos x here now. So does everybody see? This is 1, or you could have said this is 1 squared. Doesn't matter, because one of the properties is the power of a limit is the limit of the power. You could do it just as 1 squared. Okay, and then 0 goes in here. I get 0 on top. So I'm going to get 1 squared times 0 on top. And then what do I get here? What's cos of 0? Because the limit as x goes to... So sorry, what is it? Cos of 0 is 1. So 1 plus 1 is 2. And so then what do I get there? Stop it. 1 squared times 0 divided by 2. It's 0.
What? Oh, yeah.
Woo! So that leads me to this setup is equal to 0. Okay? And the reason why you can't do it directly is if you put 0 in there, cos of 0 is 1. 1 minus 1 is 0 on top, 0 on the bottom, 0, 0. So it's no, it's not indeterminate. So this, we just proved that it equals 0. And not the reciprocal, but actually like the, huh? So let's do this. So we have this. If I plug 0 in, I get 0 over 0. Everybody understand? We can't do this. So I need to set up that the 1 minus cos x over cos x. So the limit as x goes to 0 of 1 minus cos x. I'm going to scooch the sine squared over. Right? If you want, I'm going to write it separately because it seemed like you didn't understand it the other way. So I'm going to write it like this. Okay, so everybody understand this is the same exact thing that's there. It's just expanded or whatever. Okay, so in order to get this set up, I need to have what on the bottom here? I need an x at the bottom. I can't just do that. So I put an x on the top. So then what happens here? I put an x there, and then I get an x there, but what happens there? I have then a 0 at the bottom. Sorry. Yeah, this is like this, right? I have a 0 in the bottom. I can't do that. So you'll find when you do some of these, you think you're getting somewhere, and then you're going, oh, I have to start all over again. My advice to you is, if you do this and you discover that you can't get anywhere with that, don't erase it, because if you have to ask me a question the next day, I want to see what you've actually done and tried, okay? So on the AP exam, you don't have to erase it. All you have to do is go like this, and they will not mark it. Anything that's crossed off, they will not mark. And the same thing goes on my test. If you put a cross through it, I won't mark that part. But don't say, oh, the right answer is in the cross off and expect to get marked. Once you cross it off, I'm not marking it, okay? So that didn't work because, does everybody understand why that didn't work? Okay, so let's look at this again. How could we do this? Because I ended up having... I'm sorry? Yeah, you're saying change this bottom? Is that what you were saying? Yes. Okay, so let's try that. You guys have all these things in your back pocket. You have lots of things to try. You could do the conjugate, but we're trying this right now. We're changing sine squared x into 1 minus cos squared x. Okay, so... And then we learned in grade 12 that this is something you can factor, right? Oh, yeah. I thought that's what you were going with it. Well, I was thinking, well. So this is 1 minus cos x times 1 plus cos x, yes? Does everybody see what I did? So these will cancel. Now we're going to do the limit. 0 goes in here. What's cos of 0? 1. What's on top if that's canceled? A 1. And then I have 1 plus 1, which is 2. So then I get 1/2. So I guess what I'm trying to say is, just because I showed you something doesn't mean every question you're going to be doing is that setup. You're going to have to really analyze what's going on. Again, if something doesn't work, like you attempt something. So for instance, on this one, somebody said multiply the conjugate. Try it. See if you get anywhere. You might. You might get the same answer the same way. If you do it right, you'll get the same answer. I'm not saying that the conjugate won't work. I'm just saying we were trying it this way and it ended up working. Next one, I think, or the last one, I should say. It's interesting you guys like me separating it. One sec. Do you guys want me to separate as sine 3x times sine 3x? Do you want me to do this together? Are you sure? Yeah. Okay, it is quicker if you understand it. Okay, so I'm going to write sine of 3x, the whole thing squared. So that's the top. Yes? Everybody understand that's the top. Okay, so what's at the bottom here? It's just x, hey? Does everybody see? That's exactly the same as that. Okay, we're good. So we can't leave it like that. So what do I have to add in there? I need to put a 3 there. So what do I need to compensate over here with? Huh? A 9. Because that's not just a 3, that's a 3 squared. So this is a 9 on top. So this is my 1. So 1 squared times 9 is 9.